In this section, we're going to discuss the electron configurations for only the outermost shell, which are the electrons that are involved in bonding. On this slide, we will show how to go about writing electron configurations and use the abbreviated method for describing electron configurations. Initially, we have here the electron configuration for helium. Helium has 2 electrons, its atomic number is 2, and so the outermost shell is represented as 1s2, so its electron configuration is shown in red. If we go to an element in the second period, such as oxygen, which has a total of 8 electrons, you'll notice that the first shell is now completely filled, and we show that in blue. The valence shell is the second shell, which has 2 subshells, the 2s and the 2p. There's a total of 6 electrons in those subshells, as shown here in red. The element that is the noble gas in the second period, furthest to the right, is neon, and so in this particular case the electron configuration has 2 shells. The 1s, which is shown here in blue, is referred to as a core shell or inner shell, and the valence shell, which is the outermost shell, is the second shell and has the electron configuration of 2s2, 2p6. The next element is aluminum, which is an element in the third period. So now in this particular case, aluminum has core electrons, which are completely filled in the first shell and second shell, as shown in blue. This happens to have exactly the same electron configuration as the noble gas neon, which is the closest to aluminum on the periodic table in terms of atomic number. There are 3 additional valence electrons for aluminum that then occupy the 3s and 3p subshells, as shown here in red. If we go to the noble gas that is furthest to the right in the third period, we can completely fill up the 3p orbitals with a total of 6 electrons, and we now have a very stable electron configuration, which is true of all of the noble gases. We go to an element in the fourth period by adding 1 electron. This is potassium. In this particular case, then we have 3 shells that are considered core shells. The valence is the 4s, or the fourth shell, and so this is shown here in red. Finally, we add 1 additional electron, and we add 1 more electron to the 4s, and that fills that subshell. So we have 2 electrons. Say we have 2 electrons in the valence shell for calcium. To write the abbreviated form of the electron configurations, what we're going to do is we're going to replace the electron configurations that are in blue with the corresponding atomic symbol of the noble gas, which we place in a bracket, and then only show the valence electrons, which are shown in red. For this slide, we will describe the shorthand approaches for dealing with electron configurations and the so-called pseudo-core electrons. The electron configuration for argon is shown here. In blue, you will see the inner shells that are completely filled, the first and second shell. The third shell is considered the valence shell for argon, and that's shown in red. The total number of electrons for argon is 18 electrons. For potassium, which has 1 more electron than argon, you can notice that shown here in blue, the inner shells are completely filled and happen to have exactly the same electron configuration as argon. The valence shell, or outermost shell, shown in red for potassium, is got one electron, and it is located in the 4s subshell. It turns out that we can then abbreviate this electron configuration by placing the electron configuration for the noble gas core, which is argon. Place the symbol for argon in brackets, and then only write the electron configuration for the outermost shell, which is shown in red. For calcium, which now has 2 electrons in the 4s outer shell, we would do a similar shorthand approach by writing brackets argon, but now we would have 2 electrons in the 4s2 shell. If we go to something like arsenic, in this case we have a total of 33 electrons. Again, the core of argon is present, but we also notice that now the 3D subshell is completely filled, and so when we write the electron configuration for this particular element and use the approach, we would include the 3D electrons in the abbreviated approach, but the only electrons that are going to be involved in bonding are the electrons that are in red, because the subshell 3D is filled. So we refer to not only the argon core, but also then the 3D as the pseudo-core electrons, and therefore there would be no need to write those 3D electrons in the abbreviated or shorthand approach for